Thanks. Thank you, Doug, for inviting me. It's always really an honor and a privilege to speak to you folks. It's always humbling for me anyway. So when Doug asked me to put something together, he said, it's an ISSW year, do you have something? I said, what do you want to hear? I said, I've got some stuff I'm putting out on the explosives. And he said, well, you know, he said, I want something kind of sciencey. And so this is a new idea I've been working on. Is that right?
That's correct.
Yeah, you know, something we've only been working on about 6 months. I don't have any results. It's a new idea. This has not been presented anywhere. So this is the first time I've kind of talked about it. So I'll be interested to see what folks think. And I've got a PhD student on there, Tony LeBaron. This is his project. And so I'm going to talk just briefly about the two predominant fracture theories. I'm not going to spend a lot of time on that. I just want to show you that to contrast why this is important. And then I'm going to we're proposing a way of looking at the microstructure to predict what the critical energy release rate is in snow. And I'm going to do it analytically, and we've got an experimental program. I think everyone's familiar with, since the 70s, the McClung approach with shear, what's called a mode 2 shear failure. In recent years, he's also taken into account the slope normal. And you know, he includes a lot of elastic things there, strain softening, but then assumes a brittle fracture. I think everyone's kind of familiar with that. That's been around for a long, long time. Okay, and he's made some recent modifications to it. Dave McClung's done some really fantastic work. Then, of course, here about 2008, the anti-crack model came around with Joaquin, where he talked about this anti-crack, where looked at the role of collapse. And he took what's called a Timoshenko beam. It's a type of an elastic beam. It's a way to analyze a beam. And he put that on a rigid substrate and a rigid weak layer, rigid but collapsible weak layer. That's kind of an interesting thing in his theory that distinguishes it, I'll say. And so you've all seen this out of his paper. This is, you know, the role of collapse. So these are the two predominant theories out there, and they're kind of a macroscopic theory, right? They're a large scale kind of thing, and so it's being debated and discussed. And I really don't want to weigh in on that argument, but you can kind of see the differences here in the shear model. A lot of the deformation is in the weak layer. In the anti-crack model, what's going on in the slab is really what's critical. Okay, and then there's some quotes out of papers here where you know, McClung's saying, "Hey, we're seeing that collapse, but we're seeing it after a shear failure." And then, of course, Hirely talks about anti-crack is the rule of failure. Okay, and so in both of those theories, one of the things that come out is a material property having to do with how easy is it to fracture snow, and that material property is called the critical energy release rate. And it gets down to the critical crack length, but both those theories, that's something that comes out of them, and they're trying to determine what is that material property for how well will a crack propagate through that snow. And so we started thinking about this and thought, you know, it'd really be desirable to get that without depending on any load, without making any assumptions to any kind of mode of failure, whether it's collapse, whether it's shear, whatever the loading could be. And so that's kind of how we went off on this, because it is a material property. And so let's take a look at, and so Ed and I, you know, my background long ago was in snow metamorphism, so I'm kind of I like microstructure stuff, and so we really start thinking that what's going on has to be happening down at its fundamental level at the ice grain and bond level. That's where this stuff has to be started. So I mean, we're diving in there, and this is a scanning electron microscope image that we took many years ago for another project. We were looking at grain boundary diffusion, but this is some well-rounded snow, and this is pretty familiar to you. If you don't know what a scanning electron microscope does, it takes really high resolution, high magnification images of surfaces, and so that's what we were doing there. We actually ended up zooming in on some of these grain boundaries and looking at what was going on there. But you look, you know, it's kind of an interesting spot right here, and if you look at that spot, you notice that when we put that sample in there, it appears that there's been probably some other snow grains on the other side of those bonds there, and that the fracture happened through the bonds. And so we started taking a look at, and this has been in the literature too. There's several folks in the literature who have said, hey, the fracture in snow propagates through the interconnections between the snow grains. And so the snow microstructure, a lot of it becomes important then, being able to identify what are those bonds. Are these here's a bunch of bonds, interconnections between grains. And then what is a grain? Is that a grain? Is that a grain? You know, so we're starting to look at, you know, what are the details of the microstructure where this fracture might initiate. And so that was kind of the idea behind this. This is the plan, is we're going to use the actual microstructure to try and predict this parameter. And of course, as you would expect, the arrangement of the grains, the bonds, what they look like, what's the pore space between them, is going to be pretty critical to determining those characteristics. And so, you know, everything, you know, we have to do stuff as a hypothesis. So the hypothesis is that the microstructure dictates this process, that it's the primary mechanism that's dictating the sensitivity of snow to fracture. Okay? And so the goals are two. One is to be able to model this. Take a look at this microstructure and can we predict this based on what the snow microstructure is? And then, of course, the second one, these are going to be Tony's goals, is to do a lab experiment to validate it, but we've also got some ideas on how to do this out in the field. But we're still, like I say, we're at the beginning stages of this, and we haven't sorted all that out yet. Okay? And we've gone and looked at other fields. There are other, you know, snow is a polycrystalline material, right? Ice is a crystal. And there are other fields where they've looked at these polycrystalline type materials and looked at this problem. Ceramics is one of them. So we started looking at some of that, and what we find is in fracture, and it's well documented, that there is a path that's going to go through that microstructure that requires the least amount of energy for that fracture to propagate. I mean, it kind of makes sense if you think about it. There's lots of paths that this fracture could take, but if we could find one that took the least amount of energy and calculate how much energy that took, maybe we'd have a shot at figuring out what this material property was. Of course, you look at snow, there's a finite but very large number of possible paths that it could take, but it's not infinite. And so could we possibly find the one requiring the least amount of energy? And so that's where we kind of launched off into this about 6 months ago, I guess. And so trying to develop a model to be able to predict this, we kind of broke this up. We need to be able to first come up with representative snow microstructure. I'm going to show you, we're very proud of our, I think Ed might have shown some this morning, I'm not sure, to show some CT images. We're very proud of our CT. It's state-of-the-art kind of thing, and takes great images. And then we have to figure out what is a grain, what is a bond. If these things are going to propagate through bonds, like we think, got to find out what they are, find that path, find that path of minimum energy, right? All these paths are possible. Which is the sweet one that we want to get? So I just throw some of these CT images up here, some well-rounded snow on a 2 millimeter grid, pretty familiar to everyone in this room that looks through a hand lens. You can see what it looks like in 3D on a CT. You know, our CT imager uses X-rays to be able to make 2-dimensional and then 3-dimensional representations of the snow at very high resolution, down to about 5 microns. Okay, and so in this sample, this is almost a centimeter in diameter, just to give you an idea of the thing we're talking about. So we're interested. First off, we'll start with the easy problem, the rounded grains. We'll go to the other stuff later. How do we figure out how a fracture might propagate through that structure? And we just throw this up because it's pretty. We grow surface ore too and bury it and do testing on it. And so you can see how the CT image of surface ore, you know, you can even see the steps and ledges in the CT image. It's a great instrument. Okay. And so after we take a sample of snow, and then a representative sample, we can talk about what that is, and then we CT it. We need to get it into some sort of a computer representation to be able to start to do any kind of calculations on how it might fracture. Okay. This picture, actually, I found this. I was out in Davos last summer at a conference, and this is from Hagenmuller. The French are working on this too. There's a lot of interest in how do you go from something like this and put it into something where you identify what's a grain and a bond. And so we're interested in doing that. There's a couple of techniques you might be interested in. They're using changes in curvature, right, as I go from changes in curvature to be able to identify. We're using a little bit different method called a watershed method. It kind of identifies peaks and valleys, and the valleys are where everything's going to run, and that becomes a neck. Here are some grains that we have segmented, so we've gotten that far. We've been able to use some of these techniques and take a CT image. Those are just some rounded grains. and we've been able to identify the bonds. It's been a fair amount of work. That's a whole field, being able to figure out, the sterology and being able to get, how do I take this three-dimensional model and say, well, this is a grain, this is a bond, that sort of thing. Okay, and so I'll get into the model here a little bit. Now this is just a cartoon. Try and get you to understand the idea. So this is three-dimensional, but we'll pretend like it's two-dimensional. So now we've taken our ice structure here, and we've got a bunch of grains, and we've identified the interconnections between them. They don't have to be round, it's just the way it is. And so the question, and then what we do is we make something called a line graph. We put a node in each grain, and then we have a line connecting each grain. And so in theory, there should be a bond associated with each line if they're connected. Okay? And so the question is, where will this fracture go? It could follow maybe a path like through these three bonds, maybe it goes through here, maybe it goes down. That's the question, and of course we're going to blow this up to a very, very large scale. Like I say, this is just a cartoon, so that's the question. And so what we do is we assign each bond or line, it's pretty well known, the energy it's going to take to separate a piece of ice. That's what this gamma is. I think this is, not many equations in this, but gamma is the energy it takes, it's the surface formation energy, the amount of energy it takes to form a surface of ice. And that's well known. Okay? And if we have a fracture, we're going to make two surfaces. We're going to take something and we're going to fracture it, we're going to have two surfaces. So we need twice that. And then if we multiply that times the area of the bond, that gives us the energy it's going to need to separate a particular bond. I think that makes sense, that if we had a piece of ice, we would know how much energy it would take to separate that ice. And so what this approach does then, and these are just made up numbers, is it assigns a number to each of those by how much energy it takes to separate a particular bond. Okay? And then there's a theorem out there, it doesn't matter really what it is, but it's called the max flow min cut, and it's a way that tells you, once you've done that, how do you find what's the minimum energy to get through that. So what we've done is we've taken this, we've discretized this structure, we've turned it into a model, we've gone and measured how big these bonds are, assigned a weight based on how much energy it's going to be to do that, and then we are able to apply this other model that says, okay, this, in this case, happens to be the minimum energy path through that structure. So in theory, that's where that crack should go. Okay? So it's going to predict and say, okay, where does that crack go? Does this make sense? Everyone following along? So it says, hey, the minimum energy path is right there. Well, what we do is we take a big sample, big is big. Big, I shouldn't have said big. Can we turn that off? Big is not big, okay? But we take a representative sample. How's that? A representative sample where statistically, and it really isn't hard with snow, it doesn't take a real big sample, where we can then say, find in 3 dimensions where this path is going to go. And then we add up the energy it takes for each of those bonds along that minimum path, and out pops that quantity, a prediction of that quantity that we want. Okay? And so what it's doing is it's saying, I'm going to look at the details of the microstructure, not just how, if I laid it out disaggregated on a crystal card or something, but in situ, how it's arranged, and then what's that energy, and where would that path want to go? Now we've had some ideas here lately. We got this running, and it's working, and it will predict through a pretty good size sample. Again, good size is thousands and thousands of grains. How's that? Tens of thousands of grains. Okay, where it's going to go. But we all know that things like microcracks happen, right? We get a little bit of cracking, that goes off that doesn't result in the main path of the fracture. Sometimes called strain softening. If you're reading the literature, sometimes microcracking is what they call strain softening. And so we've got a way of doing that. We just look a little bit ahead, right? We take a little volume, look ahead, where would a crack go, then we open that volume and find out, oh, that original path wasn't the path it wants to take now, there's another one. And so we're finding ways where we can simulate microcracking with this. And so then, of course, the question is this right? And I don't have an answer for that, other than we're getting in the ballpark with some published values with this. I mean, I'll just say we're in the ballpark. We're not off by a factor of 10 or 5 or less than a factor of 5. And so we said we're going to go into the lab and try and design experiments, because we can take these snow samples CT them in the lab, and then go right in the room right next door and be able to test them and see if we're even getting close. Okay? And so we want to measure this energy release rate that I've talked about for these snow morphologies. And the project is going to look at, we're first going to start with rounded grains, but then we're going to look at radiation recrystallized and surface core weak layers that have been buried. We're not there yet. We've got some ideas on how to do that. We're just sort of getting this together now. Did you show this? Did you talk about this today?
A little bit.
A little bit. Ed might have showed this today. This is one of our standard setups that we're using right now, where we have a base layer. We grow some sort of a faceted layer on the surface. We subsequently bury it with a shear frame on top. We re-excavate the shear frame like you see here, and then we're able to put this testing apparatus on here where we can simulate a combination of normal and shear load, very, so you can get slope, angle, and load very precisely on that, whatever condition that you want. Okay, and then what we do is we watch optically what goes on in the cross section. And Ed might have showed some of these where we've got a optical strain measurement system, so it tells us the strain, and basically there's zero strain in this sample except for right along here where strain's starting to build up, and that's where that sample eventually failed. Okay. One of the things we have to modify for this project is a couple of things. One is, I'll talk about it here in a minute, we need to track everything that's going on here, right? Because if I take a load cell and I push on this, and some of these grains, I create some strain up here. Maybe the weak layer's down here, but I create some strain up here. That's energy that went into the system that's not going into fracturing my weak layer. So we have to account for all that. And so we've designed this new open-ended shear frame so that we can pretty much track all the particles that are going on in there. Now, these fractures propagate relatively quickly, 20-ish meters per second is probably what a typical fracture might propagate at. So it happens very quickly along here. And so we're using some cameras. We borrowed Carl's, and it's been very useful. And we find that everyone's using these cameras. What happens when you get the frame rate real high, right? We want to get the frame rate real high so that we can, you can't see all the little spots, the resolution sucks. So we're in the process. We just purchased, it should be here in about 3 weeks, a pretty high-end, high-resolution, high-definition, high frame rate camera to do some of this with. And so, but we're getting the process down here. And then the idea is, as this thing's loaded, I can keep track. If I could have perfect measurement, infinite spatial resolution and infinite temporal resolution, we keep track of what every little particle's doing here. We know what energy is going into, say, compressing or putting load into the slab, and we also can know what's going into the weak layer, and we can separate those things. And we can, and so that's the idea here. Our energy, so this is an energy equation. I know you guys, I guess you talked about energy or something this morning, but the energy going in is from that load cell. Okay? And you may remember energy is sometimes termed work, and work is force acting through a distance. So if I take that load cell and I push through some distance, I know the work or the energy that's going into that whole shear frame slab system. So that's the left side. That's what's going in for my load cell. U is the elastic strain energy. That's from all the stuff that's around. I'm deforming all that stuff in that slab. It may recover, it may or may not be elastic, but I put elastic on there. But that may come back, but that's not necessarily going into the weak layer. And so if we take that energy going in minus the stuff that we measured that didn't go into the weak layer, we know the area of the fracture after it's done. We know how big our sample is. We can flip it over. We know the area. I should be able to back out an experimental value for the same thing that we're trying to predict. Okay. So we're kind of, this is I don't know if this is making sense, just because this is the first time we've rolled this out, but this is kind of our thought on a different way that's mode independent. It's just it's material property, getting at one of the same parameters that the prevalent models or the prevalent approaches are trying to get at, and it's material based. We're just at the beginnings of this, and so we're modeling this without any assumptions on what the failure mode is. I mean, we're just putting a load on it. We're not saying it's mode 1, mode 2 shear. We're just putting a load on it. It looks like a slope with snow or a ski or whatever you want to put on it. You tell me the load, we can put it on there. And it's definitely based on other fields that have a similar problem. Most of the other fields don't have a continually evolving microstructure. I think that sets snow apart in complexity. And, but I'll just say there's a lot of challenges. This is really the early stages. Like if you take, let's take a surface ore grain and let's put some snow on top of it. What's a bond look like? You know, those kinds of things. And so I've got some ideas on maybe we don't want to talk about grains and bonds. Maybe we just want to look at ice, connected ice, and find where's the minimum pieces of ice that this thing would want to go through, maybe through the middle of what we might call a grain, that kind of thing. So that's kind of the 20-minute version of a new project that we're I don't know what we're doing, we're working on it. If it works, Tony will get a doctorate. If it doesn't, he won't. So pray for Tony. He's a good dude. He's had a lot to do with this. He's a great student, so we're really happy to have him. And I don't know, does that kind of make sense? You see, it's agnostic to any of the heated discussions that may be going on in the field. We're just trying to, you know, look at the very basics, figuring, well, this has to start down at the grain bond level.
Would you publish it, or if you publish it, will the energy input be in PSI or Pascal?
It'll probably be in, if it's in SI units, it'll be like Newton meters. Yeah.
How does a layperson?
Or a foot pound.
How about taps in the shoulder?
If you help me with that conversion, my wrist shoulder thing